Okay, so we're starting the final chapter of gases, chapter 12. Let's recap what we did in chapter 11. In chapter 11, we learn the relationships between volume, temperature, and pressure. They had been so thoroughly tested that they are now accepted as laws. We also saw that these laws have many applications, from breathing, filling our tires with air, to the air pressure in our ears as you fly or scuba dive. So in chapter 12, we will continue to explore laws that govern gases in mixtures and in chemical reactions involving gases. So what happens when we change the quantity, the number of molecules, or the mass of a gas? So far in chapter 11, all the gas laws required a constant amount of gas. So how does the amount change that relationship? So Gay-Lussac, he measured the relative volume of gases involved in various chemical reactions. And his observations showed that the volumes of gaseous reactants and products were always in simple whole number ratios. He was unable to explain it, but through experimentation, it became a law because it was proven over and over again. So this law of combining volumes says when measured at the same temperature and pressure, volumes of gaseous reactants and products of chemical reactions are always in simple ratios of whole numbers, just like this example below. So we had 1 mole of nitrogen gas reacts with 3 mole of hydrogen gas to produce 2 moles of ammonia, which can be translated into 1 volume of nitrogen reacts with 3 volumes of hydrogen, producing 2 volumes of ammonia when all are measured at the same temperature and pressure. So that's what's key, same temperature and pressure. So it wasn't until Amedeo Avogadro came along that he explained why this was. So he proposed that equal volumes of gases at the same temperature and pressure contain the same number of molecules. So, for example, how can 2 samples of gas contain particles of different mass have equal pressures at the same temperature? This is what Avogadro explained. So because temperature is a measure of the average kinetic energy of entities in a sample, and at any given temperature, all gas entities have the same kinetic energy, regardless of their size or mass, and the difference in pressure has to be due to the number of entities present. So if the pressure is equal, then there has to be an equal number of entities in the containers. So through this thought process, he came up with what I said already. If you have an equal volume of gases at the same temperature and pressure, they contain the same number of molecules. Now, the interesting thing was this was not accepted for 50 years. So after 50 years, and it was founded before the kinetic molecular theory, it became a law. So they did decide to name it Avogadro's law because he found it. So this law says the volume of a gas is directly related to the amount of gas, which kind of makes sense if you think about it. When the temperature and pressure of the gas remains constant again, you have equal volumes under identical conditions contain the same number of entities. Okay? So from that, we can use this ratio, and this ratio says that a certain number of entities have a certain volume. If we change the number of entities, we have a different volume. That's what that says. That says the volume of a gas and the number of moles of gas are directly proportional, right? That means change the same amount. So let's use this relationship now and check it out in a calculation. So, for example, if I have a balloon that contains 4.80 grams of carbon dioxide gas, and it has a volume of 12.0 liters. Assume that the pressure and temperature of the balloon remain constant. What is the new volume of the balloon if an additional 0.5 moles of carbon dioxide is added? Okay, so what are we given there? Okay, so we are given, we have our mass of carbon dioxide is 4.80 grams, and the volume is 12.0 liters. So that would be our V1. What is the new volume of the balloon if an additional 0.5 moles of carbon dioxide is added? So we want to know what our V2 is going to be once we've added an additional 0.5 moles of carbon dioxide. So first off, we don't know how many moles we have, right? So we have to find our N1. As our step one is going to be to find N1. So if we have a mass, how do we handle that? Well, we have carbon dioxide, so we'll need the molar mass of carbon dioxide, which is, where did I put my calculator? 16 times 2 plus 12.01. So 44.01 is our molar mass of our carbon dioxide. So we can find our N1. Mass over molar mass, which is 4.80 grams divided by 44.01 grams per mole. So we get N1 is equal to 0. How many digits do we need? Well, they have only one digit there, which I don't really like, but I'm going to put down 4 digits and keep it in my calculator. So I found my N1, I have my V1, I can find my V2. Yet, can I find it? Yes, I can. So I have my N1, so it says I've added 0.5 moles. So what's my N2 going to be? It's going to be N1 plus 0.5 moles. So I kept my number in my calculator, add plus 0.5. So 0.6091 moles. Now I can put this into my equation to find V2. N1 over V1 equals N2 over V2. Now to isolate for V2, you can flip both sides of your equation, right? So that puts the V1 on top. And then get rid of the N2 by multiplying both sides by N2. So V2 is equal to N2, which was 0.6091 moles, running out of space here, times V1, which was 12 liters, 12.0 liters, divided by N1, which was 0.1091 moles. Okay? So we're going to solve that. I've left that other number in my calculator, times 12 equals divided by 0.1091. And I get V2 is equal to, so my units of volume had 3 digits. So we're going to say 66, that's actually rounded up to 67.0 liters. Okay? That would be my V2. So therefore, the new volume is 67.0 liters. Okay? So let me get that down. I'll delete this little thing. Okay, so questions to that are similar using, you still got to use the mole, right? So we've had to keep using that mole all the way through. All right, so the last thing is molar volume. So the molar volume is the volume occupied by 1 mole of gas, and it's the same for all gases. Now, what will change the volume of this molar volume is the conditions. So if it's at STP, and that's at 0 degrees Celsius and 101.325 kPa, the molar volume is 22.4. If it's at SATP, standard ambient temperature and pressure, maybe you want to write that down, standard ambient temperature and pressure. That's the S, and this is just standard temperature. So it's slightly higher at 25 degrees Celsius, and the pressure goes down at 100 kPa. Notice the volume goes up to 24.8. So those are two numbers that you need to remember about gases. You need to know STP and SATP, and you need to know those volumes, okay? And so this diagram here is just showing various gases and how they are all at STP, and the molar volume is the same for each one. Doesn't matter if it's helium, nitrogen, or methane, same molar volume. What's different, right? The masses are different, right? But the number of gas molecules is the same. Remember that number? Avogadro's number. Okay. All right, so molar volume then, this is how molar volume is this MV equals V over N, and it's equal to the volume divided by the amount in moles. So that's what molar volume is. You need to copy that down. Okay, so let's use this equation in some calculations. So hydrogen gas is produced when magnesium reacts with hydrochloric acid. Here's your equation. So if 4.50 grams of hydrogen gas is collected at STP, what volume of hydrogen gas does this represent? Okay, well, let's work through that one. What are we given? We are given the mass of hydrogen gas, STP, so we just learned about those conditions. What does that mean? If you're not sure, go back and look. STP. So that would be our temperature is 0 degrees Celsius or 273 Kelvin, which is what we need to use, right? And when we're talking, and 101.325 kPa. So we're just reviewing those, but what does that tell us about our molar volume? We know that the molar volume is equal to 22.4, and that is liters per mole of any gas. So we want to know, what volume of gas does this represent? So if it was 1 mole, it would be 22.4 liters. How many moles do we have? That's what we got to know. So we have to find how many moles we have. Moles of hydrogen is equal to question mark. Our molar mass of hydrogen, 1.01 times 2, so 2.02 grams per mole. So moles is equal to mass over molar mass. So we have 4.50 grams divided by 2.02 grams per mole. Grams will cancel, and what are we left with? 4.50. So 2.23, because it says 2.227 moles. So how much, what does this volume represent? Well, we got to use the molar volume is equal to the volume divided by N. Well, we have 22.4 is equal to V over 2.23 moles times 22.4. So our volume would then be, we multiplied them, 22.23 times 22.4 is 49.9 liters. That's how much we have represented, which kind of makes sense, right? Right, because if we have 2.23 moles, it's double the amount of 1 mole, just a bit more, right? So there's our answer. So therefore, the volume of gas represented by 4.50 grams of hydrogen is 49.9 liters. Okay? Okay, part B of this question says if 0.52 moles of magnesium completely reacted, what volume of hydrogen gas in moles would be produced at STP? How many grams of hydrogen is this? So we got to go back to our chemical equation to check out our mole ratio, right? So we have magnesium has a 1 in front of it, and it's asking hydrogen gas. Well, we happen to luck out it's a 1-to-1 ratio, right? And that's what the note says. There's a 1-to-1 mole ratio of magnesium and hydrogen gas in the balanced equation. You have to verify that in every equation. What is the mole ratio? It might play a factor in your determining your answer. So make sure you check that. So we have our moles of magnesium is equal to 0.52. We want to know what volume of hydrogen gas would be produced. Again at STP, right? So that tells us we want to know V. Our molar volume is still going to be 22.4 liters per mole. We just now have to find out how many moles we have, right? It's a 1-to-1 ratio. So find our moles. Oh, sorry. Our mole ratio is 1-to-1. So since our mole ratio is 1-to-1, that means our moles of hydrogen is also equal to 0.52 moles. Okay? So we got to put that into our equation now. Molar volume is equal to volume over N. So we're trying to find our volume. So V is equal to molar volume times N, which is equal to 22.4 liters per mole times 0.52 moles. Mole. So the moles will cancel out. So what's that equal to? 22.4 times 0.52. So our volume is equal to 11.6 liters is what we're left with, okay? Which again makes sense because now we're halving the number. This is half, so half of 22.4 is equal to 11.6. So therefore, oh, actually, I see that we have to put that into grams. So our volume is that, so now we got to get that into grams. Okay, yeah, so we found our volume. That's part 1 of the question. Part 2 says how many grams of hydrogen is this? So that means we got to take our moles of hydrogen and put that into grams. So that's part one. So we could, yes, we do put it there for a statement. The volume of H2 at STP would be 11.6 liters. So part two is how many grams? So we first found this. We want the mass of hydrogen. So we have our moles, we need our molar mass again, which we found up above, which was 2.02 grams per mole. So mass is equal to moles times the molar mass, which is equal to 0.52 moles times 2.02 grams per mole. Get rid of moles. So put that in your calculator. 0.52 times 2.02 equals 1.05 grams. So therefore, we have 1.05 grams of hydrogen produced. Okay? Okay, so we've looked at two concepts in this lesson. We first looked at Avogadro's law. So we've now seen that the volume will change with the amount of substance. And then we've looked at molar volume, okay, which is constant for substances at STP at 22.4 liters per mole, and at SATP, it's at 24.8 liters per mole. So those are the two concepts we looked at, and there's some questions for you to do. Do as many as you feel necessary. The answers are there, and please do reach out if you have any questions. Take care.